Hello, and welcome to the section 2.4 video lecture. So far of late in chapter 2, we've been looking at limits, and we've been talking about one of the things that can be odd about limits is that they don't exist when the graph approaches an x value from two different heights when you're looking at the y values. So one of the ways to fix that is to look at one-sided limits, and so that's what we're going to talk about in section 2.4. So go ahead and take out your notes, which can be found on Blackboard or MyMathLab, and you can go and follow along as we start on page 22 of the chapter 2 handouts. So suppose a function f is defined on an interval that extends to both sides of the number c. In order for f to have a limit L as x approaches c, the values of f of x must approach the value L as x approaches c from either side. Because of this, we sometimes say that the limit is undefined. If f fails to have a two-sided limit, I'm sorry, that's not the right word there. Two-sided is the word I was looking for. Two-sided. If f fails to have a two-sided limit at c, it may still have a one-sided limit. That is, a limit if the approach is only from one side. If the approach is from the right, the limit is a right-sided or right side limit. Or from the left, it's a left side. Or I think the word I actually wanted is left hand. Here too. Let's go back here. Let's make this right hand. If we can only consider the values of f of x on an interval c comma b, where c is less than b, and the values of f of x become arbitrarily close to L as x approaches c from within the interval, then f has a right-hand limit, L, at c. And in this case, we write the limit as x approaches c with a little plus in the numerator of f of x equals L. So this little plus symbol, which we also see here, means that we consider only values of f of x for x greater than c. So we're only thinking about x values that are greater than the value we're looking at. So we're only looking on the right side. Similarly, we can do the same thing for limits on the left, but in this case, we use a negative in the exponent of c. And that just means we're only considering values that are less than c, so we're only looking at the left-hand side. So we can also talk about, now, one of the ways all these limits we've talked about are related to each other is through the following theorem. So suppose that a function f is defined on an open interval containing c, except perhaps at c itself. Then f of x has a limit as x approaches c if and only if it has a left-hand and a right-hand limits there, and these one-sided limits are equal. So the limit as x approaches c of f of x exists if the limit as x approaches c from the right is equal to the limit as x approaches c from the left. And in fact, that limit would be L. So both of these would equal L. So they'd all be equal to each other if they're all the same. So we can also talk about the precise definition of these. So assume the domain of f contains interval c comma d to the right of c. We say that f of x has right-hand limit L at c, and write this limit if the following is true. If for every epsilon greater than 0, there is a corresponding delta greater than 0, such that when the absolute value of f of x minus L is less than epsilon, whenever c is less than x, which is less than c plus delta. Okay, so that's really the same as our precise definition of two-sided limits. The big difference here is that since it's only a one-sided limit, I only have to consider what happens if we add delta, not what happens if we subtract it. So I don't have to worry about absolute values for that piece. Similarly, we have a left-hand limit, L at C, and we can write it like that. If for every epsilon greater than 0, there exists a corresponding delta greater than 0, such that f of x minus L is less than epsilon whenever C minus delta is less than x, which is less than C. So now here we're only pinning these things in on one side. So here's some good examples where we can talk about this idea of one-sided limits. So I've given you a fairly odd graph up here to look at this idea. So the first one says the limit as x approaches -1 from the right. Well, in general, -1 wouldn't have a two-sided limit because we're only able to come to it from one direction. It only has a graph on the right-hand side. But because we're doing the right-hand limit, that means this limit does exist. So that would be true. That does equal 1. Okay. Whereas if I skip down here to letter K, it says the limit, that's not the one I wanted to look at. Whereas if I said, let's just go and write it, it's not here. So, whereas if I said the limit as x approaches -1 from the left of f of x equals 1, that would be false. Because while the value of the function at -1 is 1, there's nothing to the left of it. So there's no way to approach it from the left. So that doesn't even actually exist. Okay. And so then we could go from there. So based on what you know about limits, what I'd like to suggest is at this point, go ahead and pause the video and try all of these. So they're all true or false. So if you're not sure, just take a guess, your best educated guess. And then when you're done doing that, hit play and we'll go through them together. Okay, so now that you've had a chance to try these, let's run through these. So the first one says the limit as x approaches 0 from the left equals 0. Well, that's true. Right, because as we're coming along the graph, getting closer and closer to 0 from the left-hand side, the y values are also getting closer to 0. So the second one would be false. So even though the function value at 0 is 1, the graph doesn't approach that, right? The graph is approaching 0. So in this case, the limit as we approach 0 from either direction, those are the same. So that's true. And because those are the same, that means the limit as x approaches 0 from either direction exists. So that is also true. And then since the limit for both from the right side and the left side was 0, the limit in general, therefore, is 0. And so that means that g is false because we already said that it was 0. The limit as x approaches 1 equals 1. Well, that's an interesting thing. As I approach 1 from the left, I get 1. But if I approach 1 from the right, so as I get closer to the 1, I get 1. As I come from the left, though, I get 0. So its limit is not 1, so that's false. And its limit is not 0, so that's also false. Okay, so what that tells us is that one of the things we know here is the limit as x approaches 1 of f of x does not exist. Because the left and right side limits are not the same. The limit as x approaches 1 from the right of f of x here was 0, right? If we're coming along from the right, we're closer and closer to 0. And the limit as x approaches 1 from the left of f of x was 1. So since those are not equal to each other, the limit as x approaches 1 does not exist. The limit as x approaches 2 from the left does exist, but it's not 2, it's 0. So this would be false. The limit as x approaches -1 from the left does not exist, and that's true, right? We already talked about that. If we're approaching -1 from the left, there's nothing over there to approach from, so that's true. And then the limit as x approaches 2 from the right equals 0 would actually also be false, because the limit at 2 could be 0, but unfortunately there's nothing on the right-hand side of 2. Okay. So at this point, we've talked a little bit about these, so why don't you all go ahead and pause the video and try these problems and see what you think. Okay, so this first problem is all about this idea of one-side limits being equal and therefore a two-side limit existing. So if we look at the first one, we want to look at the limit as we come from 2 on the left and on the right. Well, the limit as we approach 2 on the right is 2, right? On this piece, as I get closer and closer to 2, I'm getting the y values are getting closer and closer to 2. And the limit as we approach it from the left, well, if I come down the graph on the left side of 2, I'm actually getting closer and closer to 1. So does the limit as x approach 2 exist? The answer to that is no, because the limit as x approaches 2 from the right of fx does not equal the limit as x approaches 2 from the left of f of x. So therefore, the two-side limit does not exist. However, if we look at 4, when we come from the left-hand side and get close to 4, we get 3. And when we come from the right-hand side, we get 3. So both of these limits are 3, and therefore, yes, that limit does exist. The limit as x approaches 4 on the left is equal to the limit as x approaches 4 on the right. And those are equal to 3, so this limit would be 3 as well as the two one-side limits. Okay, and then the bottom one here. Does the limit as x approaches 0 from the right exist? And the answer to that one is no, because we've looked at this briefly in a previous section. It oscillates too much. So no, it oscillates too much. So basically, as you get closer and closer to 0, you're approaching every point between 0 and -1. Okay, does the limit as x approaches 0 from the left exist? And the answer to that is yes. That limit is 0. Right? If we're coming in here from the left, we're approaching 0. And then last but not least, does the limit as x approaches 0 from f of x exist? And the answer to that is no, because the previous two limits are not equal to each other. Okay, and so now we can start using graphs to help us out here a little. So let's see if we can graph this first equation. Okay, so the first piece was the square root of 1 minus x squared. And we want to set its domain. So let me pop back over here to the notes real quick. So that's from 0 to 1. So set domain from 0 to 1. Okay, then the next one is 1. So we can just say 1. Actually, let's do y equals 1 to make sure that graph's right. And then we can set its domain, which was from 1 to 2. And then the last one is y equals 2. Okay, and that only happened at 2. Okay, and you can't actually see it here, but you'll notice that you only get the value 2 at 2. Okay, so that's what this graph looks like. And so now we can talk about its limits. And actually, let's go ahead and I'm just going to go ahead and take a screenshot of this and add it to the notes. Okay. Okay, so this graph looks like this, and you can see it there. Let's just make these a little darker. Okay, and then I'll add in that last point that kind of went away there when we tried to graph it by hand. So now the question is, what are the domain and range of f? Well, the domain goes from 0 over to 2. Right, we get x values from 0 over to 2. The range is a little odd. So what's the lowest value? Well, the lowest value is 0. And then we go up to 1. But then we skip over everything between 1 and 2, but we get 2. So it would look like that's how we would write that range. And so the question is, at what point, if any, does the limit of f of x, the limit as x approaches c of f of x exist? So basically, anywhere that there isn't an endpoint or a jump would be where the limit x approaches c of f of x exists. So it exists on the interval from 0 to 1, but not at 0 and not at 1, because at 0 we get an endpoint, and at 1 we have a jump, so the two-side limit doesn't exist there. And then from 1 to 2, but once again not at 2, because there we have a jump. So at what point does the right-hand limit exist, but not the right-hand limit? So the only place that we have a limit on the left side, but not the right, would be over here, right? So the answer to part C would be at 2, right? Because the left side, we've got something happening. It's approaching 1. But on the left-hand side, I just have a dot. Right-hand side, I just have a dot. And then the answer to part D, where does it have a right-hand limit but not a left-hand limit? Well, that would be at 0. And then one other place that it has left and right-hand limits but not a two-sided limit would be at 1, right? Because there's a jump there. Okay, so that's the idea for that. So I think we're going to go and skip the last one here. So the next thing we want to do is we just want to find these two-sided limits. Now, one of the interesting things about these is there are a few different things that could happen. So the first thing you probably want to do when you're looking at these is graph them. Okay, so let's go ahead and graph this first equation. So I'm going to get rid of all the stuff I graphed before. So x divided by x plus 1, I believe was the first equation. I mean the first expression. And then 2x plus 5 divided by x squared plus x. Okay, and so there's the graph. So now it wants us to find the one-sided limit at -2. So let's look at our graph, and we can see what's happening here, hopefully. For some reason it's not letting me click, and okay, there, I can do it with my pen. So we can see that at -2 there is some limit. Now in this case the calculator's not telling me what it is, but I can tell that the graph has a limit around -2. Something is happening at -2. Okay, so let's go ahead, and now what that means is most likely I can do this by hand. In fact, I can probably just plug the value in, right? Because that's one of the things we know about limits. So this is probably just -2 over -2 plus 1 times 2 times -2 plus 5 over -2 squared plus -2. Okay, so that's -2 over -1 times -4 plus 5 over 4 plus -2. So that's 2 times 1 over 2. And so that's just 1. So that's the limit there. Okay. So if it doesn't have a little jump there, you're not going to have to worry about what happens at those limits. Okay, so then we could try the next one there. Okay. So let's go and try and graph that. So that one was the square root of 6 square root of 6 minus the square root of 5x squared plus 11x plus 6 all over x. Okay. And what we're looking for here is we're looking for the limit as we approach 0. So there is a place in this graph where there's a jump, but it's not at 0. Okay, so you could actually probably almost use the calculator to try and figure out what that limit is. Okay, but it's going to be a decimal, so we're probably going to need to plug in the value to use the our rules again about limits. Okay, so in this case, we have a 0 in the denominator, so that's a problem. So remember, we're going to multiply by the conjugate. Okay, and so when we do that, we get the limit as h approaches 0 from the right. Now notice, I saw that there wasn't a jump there, so the limit as we come from the right is going to be exactly the same as the limit we come from either direction. So that's why I can just use my normal limit rule. So this would be 6 minus 5h squared plus 11h plus 6 all over h times the square root of 6 plus the square root of 5h squared plus 11h plus 6. And so now we can simplify. So 6 minus this expression, 6 minus 6 is 0. So I'm just going to get the limit as h approaches 0 from the right of negative 5h squared minus 11h over h times the square root of 6 plus the square root of 5h squared plus 11h plus 6. And then we can cancel out an h. So this will be the limit as h approaches 0 from the right of negative 5h minus 11 over the square root of 6 plus the square root of 5h squared plus 11h plus 6. And now we can just plug in 0. So it's negative 5 times 0 minus 11 over the square root of 6 plus the square root of 5 times 0 squared plus 11 times 0 plus 6, which is negative 11 over the square root of 6 plus the square root of 6, which is negative 11 over 2 root 6. And so there's the limit. And if you wanted to, you could check that to make sure it matches up with our graph. Now, one of the interesting things you may have noticed while we were doing that problem is these problems is with the first one, we probably should have been able to find this limit 1 using the graphing calculator, but it didn't work out. And one of the things sometimes when you're using apps is sometimes they're glitchy with different types of problems. So one thing you may want to do that I'll point out here real quick before we do that last problem is you may want to have at least a couple different ways to graph things available to you. So if I go to my app store here, hopefully, okay, and down here at the bottom, it's working. So I can type in GeoGebra is another example of a graphing calculator app that may be useful to us. So if you go ahead and download that, it's another free app. And we'll just go ahead and give that a second. Hopefully it'll download pretty quick, but it's always good to have a backup app available. So this is a good one. There's plenty of other ones that you could use. You could have a TI-83 or 84 you use. There are websites that you can graph with. But these would all be good different ways to look at graphing things. So if we go into GeoGebra, it works basically the same way as the one we just did. But if I graph, let's just go ahead and use this for the last, let's use it for this one. For this first one. So is y equals x divided by x plus 1. Okay, times, and I already forgot what 2x plus 5 over x squared plus x. And if I click and hopefully click and drag on this, well, here. Isn't working the way I want. Oh wait, here we go. Okay, so if I choose slider, hopefully, and let's see. Oh, that's not what I want to do. Nope, none of that's working the way I want it to. So let's go ahead and delete. That's what I want. Okay. Oh, shoot. It deleted the wrong thing, which is annoying because this point is right there. Okay, now it's away. I don't know why I was doing that. But let's try this one more time. Okay, x divided by x plus 1 times 2x plus 5 divided by x squared plus x. Okay, and so now let's see if we can trace the way I want to. Okay, so let's try doing that. No, it's not working the way I wanted to. So, okay. But anyway, so you might have to find different apps. But you can actually look here. If we zoom in at -2, we can actually see that that limit is indeed 1. I can't get it to do what I want it to do right now, but you know, those things happen. Anyway, so there's another example of an app. So if we try graphing this, if we try doing this last problem, so let's graph that. I'm going to start by trying to use the class calc app. So let's get rid of this. So this one should be y equals the square root of 2x times times x minus 1 over the absolute value of x minus 1. And now this graph looks pretty weird. And if you notice, if I try to click on it and drag, it's not giving me any data values again, like when we did the last one. So that means it's probably not graphing quite right. So let's try graphing the same thing with GeoGebra. Okay, so let's y equals the square root of 2x divided except I want to add that, times x plus 1 divided by the absolute value of x plus 1. Well, and this one just kind of draws a graph, so that's not ideal. So none of this is working the way I want to do right now. Okay. So oh, except I did plus 1. Sorry, that's why this one's not working. I typed it in wrong. So let's do minus 1, like it's supposed to be. And then hopefully, okay, it'll do it. Okay, so here's a good example of how this graph actually works. Okay, and so what you can see happens here is that it gets broken into two pieces here. Okay, as we get close to 1, and that's where. So on the right hand side, we're going to get a positive answer, and on the left hand side, we're going to get a negative answer, and that's what's really useful here. Okay, what's going to happen is knowing that. So I can tell you already, back in the notes, that this first limit, as we approach it on the right-hand side, that one's going to get a positive answer, and this second one's going to be a negative answer as we approach it from the left. And the reason that happens is because if I break this into two parts, this would be the square root of 2x and x minus 1 over the absolute value of x minus 1. And the same is true down here. So actually, let me erase these for right now and put them over here. So that one's going to be positive, that one's going to be negative. Okay, and so what you should notice here is that the second value here is either going to be 1 or negative 1, because x minus 1 divided by x minus 1 is just 1. So that's not going to change the value, but this could be positive or negative 1, because the top could be positive or negative, and same goes for the bottom. So if I look at the graph, that tells me which answer is positive or negative, and then all I have to do is worry about this last part. So this part is going to be the positive limit as x approaches 1 of 2x, and this one's going to be the negative limit. I got that from looking at the graph, 2 over x. And so then we can just plug 1 in, and so this would be the square root of 2, and this will be the negative square root of 2. And that's the idea. Okay, so at this point, go and flip over to the next page and try doing these other two on your own, and then we'll go through them together. Okay, so let's go ahead and talk about these. So for the first one, if you graph it, you're going to see that there is no jump. So to find this limit, you can just plug the value in. So this is just going to be the square root of 0.5 plus 2 over 0.5 plus 1. So that's the square root of 2.5 divided by 1.5. And we can use the calculator to get an approximation for that. So square root of 2.5 divided by 1.5, which is 1.291 approximately. Okay, so that's all there is to that one. However, on this one, there is going to be a jump. And if we graph it, let's try doing it with the class calc one again. Okay, so this would be x plus 3 times the absolute value of x plus 2 divided by x plus 2. And so in this case, we can see that the piece on the right, and you can actually see the values here, the piece on the right is positive, and the piece on the left is negative. And this one I can actually scroll, so I can actually just use these answers. So the piece on the right approaches positive 2, and the piece on the left actually is going to approach negative 2, although you can't really see that here. So maybe we should check these values if we look at them, because it doesn't seem to be giving us the right answers. In fact, it's not giving us the right answers. So, but I do know that this piece on the right is positive, the piece on the left is negative. So then this would just be the limit as x approaches negative 2 of x plus 3. And this will just be the limit as the opposite of the limit as x approaches negative 2 of x plus 3. So that would be negative 2 plus 3, which is 1. And this will be the opposite of negative 2 plus 3, which is negative 1. Okay, so sometimes you have to be careful when using technology. It might not always work out exactly the way you expect, but you can use the technology plus what you know about calculus together to get the correct answer. And that's what we're doing here. Okay, then the last thing that's in this section is just a theorem that's very useful in finding limits with trig functions. So the theorem here is that the derivative, the limit as theta approaches 0 of sine theta over theta is 1. So if you can rewrite a trig expression using this idea of sine theta over theta, it can help you find limits pretty easily. So like for example here, in this first one, this is the limit as y approaches 0 of sine 3y over sine 4y. Okay? And so one of the things we want to be able to do is we'd like to be able to rewrite this so that it is using this technique over here, okay, on the right-hand side. And so what we're missing here on the bottom is we have 4y instead of 3y. And so one of the ways we can change that to write it so it's sine of something over that thing is to multiply this one by 3 over 3. So it's the limit, because 3 over 3 is 1, so that doesn't change the value of the function. So this would be the limit of 3 sine of 3y over 4 times 3y. So that's the limit as y approaches 0 of 3/4 times the limit as y approaches 0 of sine of 3y over 3y. And we know that the limit of 3/4 is 3/4, and the limit as sine of 3y over 3y is 1 from the theorem. So that would just be 3/4. Okay. And so that's the kind of thing we're going to need to do. And sometimes that's going to involve rewriting expressions in different ways. So for example, in the next one here, I have tangent of t. Well, tangent is not sine, but we can rewrite tangent as sine. So this would be the limit as t approaches 0 of 2t over sine t over cosine t. Okay. And then, so that's the same thing as So we're dividing by a fraction. So that's the same as multiplying by the reciprocal. So this would be limit of t approaches 0 of 2t times cosine t over sine t. And so now I can start to get in this sine t over t idea that we're going to use here. So by rewriting this as 2, so the limit as t approaches 0 of 2 cosine of t times t over sine t. And then I can rewrite this as sine theta over theta or sine t over t by taking the reciprocal. And I do that by using exponents. So this will be cosine t times sine t over t to the negative first. And now we can use our limit rules so that this is 2 times the limit as t approaches 0 of cosine t times the limit as t approaches 0 of sine t over t to the negative first power. And now we can simplify. So this would be 2 cosine of 0 times 1, right? Because this to the negative first power, which is 2 times 1, which is 2. Because the cosine of 0 is 1, and 1 to the negative first power is just 1. Okay, because 1 to any power is just 1. And a lot of times, okay, so that's the idea there. So that was using a fairly basic trig identity. But a lot of times they're going to expect you to use more complicated trig identities. So let's go ahead and look at some of the more complicated, using some of the more complicated trig identities here. So, for example, here we have a sine of 2 theta, which makes you think that you may want to use one of your trig identities for sine of 2 theta. Well, sine, let me use a different color because this is close here. Sine of 2 theta is equal to 2 sine theta cosine theta. All right. So now we want to replace that in the function. So this will be the limit as theta approaches 0 of 1 minus cosine theta over 2 sine theta cosine theta. And then the part on top here actually looks a lot like another trig identity that we may be familiar with, except that it doesn't have a squared on it. Well, a way we can get that in there is multiplying by its conjugate over itself. So now this would be the limit as theta approaches 0 of 1 minus cosine squared theta, which is another trig identity that we're going to use, over 2 sine theta cosine theta times 1 plus cosine theta. And then this function on top is part of this trig identity here, which is 1 equals sine squared theta plus cosine squared theta. And so now what we can do is replace 1 minus cosine squared theta is the same thing as sine squared theta. So this would be the limit as theta approaches 0 of sine squared theta over 2 sine theta cosine theta times 1 plus cosine theta. And the nice thing about everything we just did there is now we can actually start to simplify this down to something that we can use the identity we've been talking about it. In fact, in this one, I don't even think we have to use the identity that was up at the top of the page, but it works out in a similar way. So we can cancel out a sine, right? So this would be the limit as theta approaches 0 of sine theta over 2 cosine theta times 1 plus cosine theta. And now the denominator is not going to be 0 when I plug in 0, so I can just plug it in. So this would be sine of 0. Oops, sorry. Not of theta. Sine of 0 over 2 cosine 0 times 1 plus cosine 0. So that's 0 over 2 times 1 plus 1, which is just 0. Now, this one is probably a good example of something where we may want to just look at the graph instead of going through all that work. So if I graph this, okay, so 1 minus cosine x, hold on, I need the whole thing to be on top. So 1 minus cosine x over sine x. You could see as x gets close to 0, you get close to 0. So that's a lot quicker method for doing this. So don't be afraid to graph it and see if that'll help you find the limit instead. Okay? So now let's go ahead and look at the next page. So why don't you go and pause the video and try doing these ones. And once again, if you want to use the graphing function on your calculator to help you with these, you can. But you can go ahead and try these. Okay, so now that you've tried these, let's go through them together. So notice here what's inside sine on top is what's on the bottom. So that's just using the theorem. So that's 1. That's all there is to that one. Second one, rewrite this as sine 2x over cosine 2x over x. To divide fractions, you multiply by the reciprocal. So sine 2x over cosine 2x times x. 1 over x. And I'm still doing the limit. Sorry, I forgot to write that. Okay. So then this would be one thing we can do here is you should notice now that we have a sine 2x on top and an x on the bottom. So on the bottom, we're just missing a 2. So multiply by 2 over 2. And so this will be the limit as x approaches 0. And now I want to rewrite this a little because I want to write the part with the sine and the x together and the part without. But let's just write it all together first. So this would be 2 sine 2x over cosine 2x times 2x. Okay, and now I can break it into two pieces. So this will be the limit as x approaches 0 of 2 over cosine of 2x times the limit as x approaches 0 of sine 2x over 2x. The first one, you want to plug in x, so this will be 2 over cosine of 2 times 0 times the limit of 2 sine 2x over 2x is just 1. So this is 2 over the cosine of 0 is 1. So 2 over 1 times 1, which is just 2. Okay, and then for the last one, we can just look at this kind of, I think, similar to the one we did previously. But actually here what we want to do is we want to break this up into two pieces. So since I'm dividing by sine x for both, I can break it up. So this is the limit as x approaches 0 of x over sine x cosine x plus the limit as x approaches 0 of x cosine x over sine x cosine x. And so on the right-hand side, the cosine x cancel. And now in both instances, I have x over sine x. So I can flip that over using the reciprocal. So this would equal the limit as x approaches 0 of sine x over x to the negative first times 1 over cosine x plus the limit as x approaches 0 of sine x over x to the negative first. And now use the theorem and plug in 0 into cosine. So this would be 1 to the negative first times 1 over cosine of 0 plus 1 to the negative first. So that ends up being 1 times 1 plus 1, which is 2. Okay, and so that's it for this section and for this week. So don't forget to do the homework and the weekly quiz. And if you have any questions or anything like that, feel free to email, text, or call me.